If you think a bigger phone battery means a bigger fire risk, you're probably wrong. Break time equals 0. 6 is slash because of one chip almost nobody checks. It runs 8,500 mAh under 3 rules. Here's the real problem. A lithium-ion cell is a thin pouch of chemistry that only behaves inside a narrow window. Push it outside, too high a voltage, too much heat, and it swells or vents flame. That fear is why phones stalled at 4,000 to 5,000 mAh for years. Denser silicon-carbon chemistry, plus one smart chip, finally let 8,500 mAh come back. So what's the chip? Start here, nothing reaches the battery directly. Between the cell and the rest of the phone sits a gatekeeper called the Battery Management System, or BMS. Every drop of charge going in and every drop coming out passes through it first. Think of it as a bouncer at the only door. The BMS is wired to 3 sensors on the cell. One reads voltage, the electrical pressure. One reads current, how fast charge is flowing. One reads temperature. And it doesn't check once. It samples all 3,000s of times every second, faster than you can blink. From those readings, it enforces one core idea: the safe operating window. That's a set of bounds the cell must stay inside. A voltage it can't rise above, a temperature range it can't leave, a current it can't exceed. Inside the window, the chemistry is calm and predictable. Step outside any edge, and the cell starts down the road to swelling or fire. The BMS is the enforcer of all 3 of those rules at once. Nothing charges, nothing discharges without its permission. So the whole trick isn't a magic battery. It's a chip that never stops watching. But watching what exactly, and what happens when a reading goes wrong? Start with pressure. Rule 1: voltage. A lithium cell has a ceiling and a floor. Charge it above roughly 4.45 volts, or drain it below about 3.0 volts and you break it. The ceiling is the dangerous one. Push voltage too high and lithium stops tucking neatly into the electrode. Instead, it plates out as raw metal, growing tiny needle-like spikes called dendrites. Those spikes reach across the thin separator between the 2 sides of the cell. When one touches the other side, you get an internal short. A hot, uncontrolled dump of energy that can run away into fire. Here's the mechanism that stops it. Early in a charge, the BMS pushes a steady, strong current, the fast part you see on the charger. But as the voltage climbs toward that 4.45 ceiling, it switches modes. It holds the voltage right at the limit and lets the current taper off on its own, smaller and smaller, until the cell is topped up without ever crossing the line. Engineers call it constant current, then constant voltage. And the instant the cell hits full, the chip simply cuts charging off. No trickle over the edge. That's why your phone slows down at 90%. It's not broken. It's the chip refusing to plate metal. But voltage isn't the only thing that turns a cell dangerous. Now the second thing that can turn a cell dangerous: temperature. Lithium chemistry has a comfort zone. While charging, the cell wants to stay roughly between 0 and 45 degrees Celsius. Heat is the accelerant. Every reaction inside the cell speeds up when it's warm. A hot cell pushed with fast charging is the textbook recipe for swelling and venting. So the BMS keeps a tiny heat sensor, a thermistor, pressed to the cell. When that sensor reads too hot, the chip doesn't ask nicely. It throttles the charge speed or pauses charging entirely and waits for the cell to cool. That is exactly what's happening when your phone is fast charging, gets warm in your hand, and suddenly slows to a crawl. It isn't a glitch. The chip chose heat safety over speed. Cold is the opposite trap. Charge a cold cell fast, and lithium won't absorb into the electrode properly. It plates as metal again, the same dendrite danger from Rule 1. So below freezing, the BMS blocks charging outright until the cell warms up. Same enforcer, opposite edge of the window. 2 rules down: pressure and heat. But a cell can sit at a perfect voltage and a perfect temperature and still be pushed too hard. So the third rule watches something else entirely. Rule 3: current and the long game of health. Even inside safe voltage and safe heat, shoving charge in or pulling it out too fast makes its own heat and stress. So the BMS caps the peak current, a hard limit on how many amps can flow at once. And it plays a longer game. A cell ages every cycle. Its true capacity slowly fades, and its ability to take a hard, fast charge fades with it. The chip tracks this. It quietly reduces fast charging as the cell gets older. It constantly re-estimates the real state of charge, because a tired cell that reads 80% may only be holding 70. This is also where swelling actually comes from. Break these limits again and again. Too much current, too much heat, too high a voltage, and the chemistry gives off gas. That gas has nowhere to go inside a sealed pouch, so the pouch puffs up. The bulge you've seen in an old phone is that gas. Enforce the 3 rules faithfully, cycle after cycle, and an 8,500 mAh pouch stays flat and safe for years. That's the whole job. Not one heroic save, but 3 limits held a few thousand times a second for the life of the phone. So put the 3 together. Here's where it all clicks. Break time equals 0. 6 is slash voltage, temperature, current. 3 numbers, 1 chip, watched a few thousand times every second, and clamped the instant any of them drifts toward the edge. That continuous policing is the entire reason a giant 8,500 mAh cell can be as safe as a tiny one. The battery didn't get bigger because the chemistry suddenly became safe. It got bigger because the management got smarter, and because denser silicon-carbon chemistry packs more energy into the same pouch. The raw cell is exactly as touchy as it always was. The difference is the enforcer never sleeps. So flip it around. When a phone does swell or worse, catch fire, it almost never means big batteries are dangerous by nature. It means the BMS failed to enforce a rule, or a physical defect inside the cell shorted it out before the chip could react. The size was never the villain. The watchdog was. One chip, three rules. Voltage, temperature, current. That is what quietly runs 8,500 mAh without swelling or fire. Here's the next question that opens up. That same chip is where fast charging strikes its bargain, trading a little battery lifespan for speed. Or ask what silicon carbon actually is. Pick one and we'll open that box next.